Hello students, hope you are doing well. So today we are going to study the structure linear and non-linear analysis. Okay, and we are going to solve both the problem. First is structure linear analysis and another problem with structure non-linear analysis. So what is the difference between the linear and non-linear analysis? The source of this non-linearity can be attributed to multiple system properties. For example, materials. Okay, if you same bar is there having different materials, then geometry of the bar is changing. Suppose then non-linear loading and the constraints. Okay, so some of the non-linearity. First is the geometric non-linearity. In analysis involving the geometric non-linearity, changes in the geometry as the structure deforms are considered in formulating and constitute equilibrium equations. Okay, then many engineering applications such as metal forming, tire analysis and medical device analysis required the use of large deformation analysis based on the geometric non-linearity. Okay, that means their geometry is not their cross section is varying, their geometry is not non-uniform. Okay, then some deformation analysis based on the geometric non-linearity is required for small applications like analysis involving cables. Okay, then arches and sails. Next is a material non-linearity. So material non-linearity involves the non-linear behavior of the material based on its current deformation, the deformation history, rate of deformation, temperature, pressure, and so on. The examples of nonlinear materials model and a large strain, viscoelastic plasticity, and hyperelasticity, rubber and plastic materials. Okay, these are the nonlinear materials. Okay, then non-linearity, another example is that if we are doing the single bar and having using the different cross section and having different material, so their Young's modulus is different, so that is also a non-linearity in the analysis. Then constant and constant non-linearity. The constant non-linearity is a system can occur if the kinematic constants are present in the model. The kinematic degree of freedom of the model can be constrained by imposing restrictions on its movement. Okay. Now, if you want to see the uh, geometric nonlinearity example, I will show you. So you can see here. So here, this cross sectional is changing. It is not uniform. Now it is looking uniform, but I have. You can, if I make it XY view, so you can see. So here cross section is changing. It is not the uniform in all direction. Okay, let's start the structural analysis problem in Lisa software. So we have to make the one we have to take the nodes and we have to make one model. Okay, and one end of this bar is fixed and it has uniform cross section and 1000 Newton force is applied at one end and it has Young's modulus is 30,000 kilonewton. This is given. So let's solve it in the Lisa software. Now let's start the plate or shell element linear structure analysis. Okay, after that we are going to see the non-linear structural analysis. So in linear, let's start it. So here edit. So here we have to say static. Okay. Now create the nodes. So here first node is at 0 0. Add. Second node is at Z1. Say add here Z2. Add. Next is Y 0.5 x0 y 0.5 z2 add. Next is y1 z2 x0 y1 z2 add. Next is x0 y1 z1 add. Next is x0 y1 Z0 add. Next is X0 Y 0.5 Z0 add. Okay, so close it. Now you can see there are 8 elements are there. Now next is new element. So here we are going to see quad shell element. So here we have to select 1 comma 2 comma 3 comma 4 comma 5 comma 6 comma 7 comma 8. Say add, close it. Okay. After that we will select the face, select it all the elements. Now next is here we have to do extrude. So extrude, provide the thickness is equal to 10 and number of subdivision equal to 1. So it is in minus z direction, so okay. So you can see, so this is generated. Now next is the, here we have to assign the material. So assign new material. Okay. So here in the assign new material, so we have to assign the isotropic material having Young's modulus, say suppose 30 E 6 and Poisson's ratio is 0.3. Close it. Now let's okay view. This is, now let's rotate it. Now select the face, select this face and load and constraint, apply the fixed support. So here apply the fixed support, say okay. Now show isometric. Okay, so here fixed support is applied to the one end. Now next is the element. So here select this middle element. Okay. Now once you select this middle element, then click on the load, say new force. So here we have to apply the force, that is minus 1000 Newton in y direction. Okay, so in, say okay, 1000 Newton force is applied. Now let's solve this. So generate the solution, solve it. Okay, so you can see, so what is the, you can see the displacement, maximum displacement is here, and that is 0.0046 x displacement. So y displacement is also here, that is minus 0.04854. So if you check the Von Mises stresses, the Von Mises stresses, maximum stresses is 1.452 E4 E04 E4. That means 1.452 into e raised to into 10 raised to 4. Okay, so this problem we can solve it. So if you want to check the nodal coordinates update, okay, so this is the things. So you have completed this problem. Now let's do it in the non-linear structure analysis. Okay, so I will save it, save linear 1, save. Next is we are going to start new. Now let's take the example of non-linear structure analysis. In that we are going to use the 3 shell element having length 3 3 and 4. with different geometries. Okay, so it will be geometric non-linearity, and we are assigning the isotropic material to all the elements. Okay, with 21 different Young's modulus value. Okay, so material is also non-linearity. So let's solve this problem in the Lisa. Start non-linear structure analysis in Lisa software. So here we are going to select edit statics. So here we have to select 3D statics, static 3D. Okay, next is we have to create the nodes. So first is a 0 0. Okay, second node is at the y direction, that is 0.25, add, then 0.5, add. So in y direction 0.25, add. So here 0, here 0.5, 0.5, add. Now again 0, 0.5, 0.25, add. So 6 nodes are added. Now we are going to add 7 node here, that is x0, 0.5, y0, add. Now y 0.25, x0, z0, so add. Now 8 elements are added, so we'll close this loop. Now next is elements. So we have to say quarter 8 shell elements. So 1, 2, 3, 4, 5, 6, 7, 8. So add it. Now close it. Okay. So now all the elements are added. Now select it, say extrude. So we have to, where is extrude? Here, extrude. So we have to provide the thickness 3 mm in minus x direction, say okay. So now it is extruded. Now next is rotate it. Okay, now select this face, say mesh tool, so scale. So we have to scale it. So we have to scale in such a way that, okay, so x dimension will be remain same. So we will change y, say 1.5, 1.5, say okay. Now here the scaling is done. Now next is select the face, then extrude. So here again we are going to extrude. Okay, again minus 3 in x direction, thickness. Okay, number of subdivision is 1. Say okay. Now it is extruded. Again select this face, mesh tool, select the scale. So we are going to do the scaling. So here we are going to scaling, that is factor is 1, y is 2, z is also 2. Say okay. Okay, now select this face, select this face, say extrude. So now we have to extrude it in the again 4 mm thickness in minus x direction, say okay. So this is extruded. Now next is, so we have to apply the material. So here I'm going to select here three elements are there, assign new material. So here the material I have to select the isotropic because we are going to for the non-linear structure axis. So here the cross section is also non-linear and the material properties, okay, their Young's modulus is also non-linear. So here we can say we have to write down here this matrix, elasticity matrix. So here 30 E6, next is 21 E6, next is 28 E6, next is 32 E6, next is 27 E6, and last is 26 E6. Here 28 E6, 32 E6, 27 E6. What is E6? E6 nothing but the 10 raised to 6. 25 E6, that is 25 into 10 raised to 6. 23 E6. Next is 30 E6, 21 E6, 28 E6, 31 E6, 29 E6, 24 E6, 28 E6, 30 E6, 24 E6, and last is 28 E6. Now if you calculate there, I think 21 is there. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21. So 21 Young's models we have to put. Okay, so let's close it. Okay, close it. So we have applied the material also. So everything is applied. Now what is next remaining? So we have to apply the loads. So now I am going to apply the loads. So I will select this face, select it, say load and constraint, fixed support. So this is the fixed support I am applying here. So now it is fixed support is applied. Now next, no, nodes. So here I will select this node, load and constraint, apply new force. In previous linear equation also we have applied the minus 1000, okay, 1000 kilonewton in y direction, minus y direction. Okay, okay. So next is, so we have to solve this. So I will say solve it. So it will generate the solution. So close it. So you can say displacement in x, displacement in y. Okay, so displacement in y is equal to, here maximum displacement in y occurs. Okay, you can see these stresses are non-uniform. So what is one mesh stresses? So these are the one mesh stresses. One mesh stresses is red is there. There is one mesh stresses is high. that is, so let's make it isometric view. So that is 4.932 into e raised to plus 6. That much stress is developed here. Okay, so what are the reaction forces? You can see these are the reaction forces. Why, what are the these are the nodes at this end. So if you see here, so these are the nodes 30, 34, 35, 41. Okay, so these are the node numbers. So close it. So if you take the table, so if you select the all nodes, select the all values, so update, so you can see all the nodes. Okay, 44 nodes are there, and their displacement value, y displacement, z displacement, what are the stresses, what are the von Mises stresses, principal stresses, everything data will be, you can get what are their displacement magnitude. Okay, you can copy this. So in this way we have completed this non-linear analysis. Here the shape is also non-linear, changing randomly, and also your what we can say, material, Young's models of the material is also changing. Okay, so we are going to stop here. Thank you.